All right, everybody, time for a new video and a new topic. And I suppose technically this is a new topic. It's for a new assignment. I just got finished making the videos for assignment 3.1, and then here's the first video for assignment 3.2. So technically it's something new, but I hope that it's easy for you to see the relevance and the connection to what we were just talking about on the videos I just made and on the assignment that you probably just finished if you're watching this. If you can see that connection, then that will make this much easier than it would be otherwise. Okay, now these are called optimization problems. Okay, and by optimization, you can think of that we want to maximize or minimize something. So rather than explain all the forms that that question can take, I'll just show you this one example, and then you can probably use your imagination from there. Okay, so in this example, we have this function right here that models or predicts, it might not be perfect, but models are not perfect. But we've got this equation, and it claims to model the daily production cost for some commodity. Okay, a commodity is some generally desirable item for sale on the market. Okay, so let's say that that's what this function does, the daily production cost for some commodity in dollars. Okay, and X, the input variable or the independent variable in this function, is the daily production. So like if you produce 50 per day, this function tells you what the daily cost of producing 50 items is. And this is some kind of curve, like it's not linear. It's not that for every additional unit you produce, the cost goes up by so much. It looks like by the nature of this curve that depending on your production, the cost might vary, might go up and down or something like that in some nonlinear fashion. And that there is some lowest average cost, okay? So by optimize, the question that we're proposing in this scenario is what production level will yield the lowest average cost per unit, okay? So we've got like say all these possibilities. I can produce anywhere from none to 100 units per day, let's say. But there might be some level of production that optimizes all the factors involved and gets you the lowest average cost per unit, okay? Now, it might be complicated to imagine why the factors of production are like that. You might say, well, why don't you just produce the maximum? If you can make 100 per day, make 100 per day. But it may be that somewhere in the middle is what optimizes, like I said, all the factors involved. Okay, so far I've got this function that calculates the daily production cost of some commodity. And I want to know what production level will yield the lowest average cost per unit. Okay, now that's what we mean by optimize. We want to, by optimizing a cost, well, we would want to make the cost as small as possible. By optimizing, say, a profit or a revenue, we might want to make that as large as possible. So optimizing can turn out to mean maximizing in some cases and minimizing in other cases. Okay, so, all right, let's think about how we would answer such a question. And I want to do that in a way that I can tie this into what we were just talking about. So recall at the beginning of the video, I said that this will be a lot easier to catch on to if you see the connection to previous assignments and previous videos. You might think of it like this. If you want to figure out what the lowest average cost per unit is, then you might imagine that there's a graph or a curve that models the average cost. And it would have to look something like this. Why would it have to look something like this? Well, for there to be a lowest average cost per unit, there's got to be some point on the average cost curve that's at the bottom. So if I had a curve that modeled the average cost versus the daily production, then, if daily production is too high, then the cost rises. And if it's too low, the cost also rises. So, maybe somewhere in the middle is the sweet spot where we are minimizing the cost. Okay. So think of the problem like that there's this curve out there for whatever we're talking about, average cost in this case, and there's some point at the very bottom of it. Now, we've already learned how you found that point. In previous assignments, we tackled a question that was like this. Suppose you have a curve. Can you find what we called a local minimum point? That would be the point at the bottom, somewhere at the bottom on that curve. A point that is lower than all the other points around it. That's what we'd be looking for. So you can think of our question as like this. How can we find that point? Okay, well, actually, we've already learned how to find it. You can locate a local minimum point on a curve. It will be, say, at some point x is equal to c if f prime c is equal to 0. That means this number here is a critical number. And if f double prime c is greater than 0, that means that the curve is concave up at the critical number. The combination of those two things, there being a critical number at some point in question and the curve being concave up, translates to there being a local minimum. So that's all we've got to do. I've got to figure out the equation for the average cost. I need to find out where the derivative is 0. That's the critical number. And then I need to verify it's concave up. All right, and not concave down, because if it was concave down, then there'd be a maximum, and that's not what we're after. Okay. All right, let's go through those steps on this particular curve right here. Okay, so first thing, I noticed that the question said I want to minimize the average cost. So c of x, this function that was originally given, that's the total production cost. All right, total daily production cost. Average cost is like it costs so many dollars per unit, okay? Something like that. It's not the total cost for producing all the units throughout the day or something like that. So what I need to do is this. If we're going to minimize average cost, I need a function or formula that calculates or models the average cost. So the way that we learned to find that before, I remember doing this at some point, I think it was for one of the assignments for the first test, is we take the total cost function and we divide it by x, which models what? The daily production, the number of units that are produced, okay? So if we're talking about average cost, I will take c cost and divide by x. That'll be average cost. Our notation for that is usually c with a bar over it. When we see the bar, we think that means average cost. C means cost or total cost. C bar means average cost. So in my case, c of x is 0.05x to the third power minus 5x squared plus 173x. I divide that by x. That will be my average cost. Now this formula simplifies a little bit if I divide each and every one of these terms by x. X to the third over x cancels to x squared over x cancels to x, and 173x over x cancels to 173. All right, that's my average cost function. That's what I want to find the local minimum point. Okay, I'm going to find the local minimum point on that curve. And I'm not going to draw the curve to find it. I'm going to do this just by the numbers. I'm going to find a critical number on the curve and then verify it's concave up. If I can do those two things, I will know I've found where the local minimum is. Okay, and then that would serve as an answer to what production level will yield the lowest average cost per unit. Okay, so here's c bar of x. That's my average cost. First, to find the critical number. The critical number is a number, the number, where the derivative is 0. So I take my average cost, I find the derivative, which in the case of 0.05x squared, the derivative of just that element is 0.1x, minus 5x, the derivative of that element is minus 5, and then plus 173, the derivative of that element, well, 173 is a constant, the derivative of that is 0. So the first derivative of the average cost is 0.1x minus 5. I'm after the critical number, which I find by taking the derivative and setting it equal to 0. Solving that, I get 50. 50 is the critical number, okay? Now, just because I found that doesn't mean that that is where there's a local minimum on the curve. Whether that point is a local minimum or not depends on this. The curve also has to be concave up. Okay, so I've got the critical number. This may be where the answer is, but I don't know until I verify that the curve is concave up at 50. So 50 is my critical number. To be concave up is the same thing as the second derivative being positive. So I need to find the second derivative of the average cost. I need to plug in 50 to it and see if that's a positive number. If it is, then the curve is concave up at 50, and 50 is where the minimum is. Okay, so let's see. Right here, this is C bar prime. There's the first derivative. The derivative of that, let's see, what's the derivative of 0.1x? The derivative of 0.1x is 0.1. And then minus 5, what's the derivative of minus 5? Well, 5 is a constant. Derivative of that's 0. So the second derivative is just 0.1, okay? And if there's no place to plug 50 into this formula, and all that means is the second derivative is 0.1 no matter what. So if you plug 50 in, so to speak, you'd get 0.1. That's positive. So it's between these two things, okay? I need to verify that there's some critical number, 50. And then I need to verify that the curve is concave up, or the second derivative is positive at that number. If those two things happen, then I can say with confidence that there's a local minimum at x is equal to 50. Okay, so I found that point on the curve that's at the bottom. Okay, I know that this point right here that is an answer to our question happens at 50 for x. Okay, so right here, that would be 50. All right, how do I know that? It's the x coordinate, right? Because I solve for x. When I find the critical number, it's a value of the variable x. Okay, so let's do this. Let's formulate a specific answer to our question. Question was, what production level will yield the lowest average cost per unit? Okay, so that will be 50 units per day. So that's just for me to be specific with the information. You know, the number was 50, but given that this is the daily production, I'll say 50 units per day. That's how you can optimize this situation. If you make more than that or less than that, the factors of production get out of skew and your average cost shoots up from there. That's what we were able to find out. Why that is, well, I don't know. We'd have to know more about this production process. But we know that if you deviate from this number, then you will just raise your average cost. So this is the best that it can be. Okay, the nature of this production process is such that that's the best way to do it. Okay, then the next question was, what was the lowest average cost per unit? Okay, so then it's asking me for like, how many dollars per unit is the minimum number? This is like the best daily production, but to find that other number, the lowest average cost, I'd have to take this and put it into the average cost function. Okay, so let's see, average cost function, that was 0.05x squared minus 5x plus 173. So let's do that. 0.05x squared minus 5x plus 173. Okay. To find, let me make sure. Okay. To find that y coordinate, or to find what the lowest average cost per unit is, I would just need to take 50, the x coordinate, put it in there for the y coordinate. If I do that, I'll get 48. Okay, so in other words, if I do 0.05 times 50 squared minus 5 times 50 plus 173, then I get this number. Okay, so let's say this, formalize our answer. My answer to the second question is that it will be $48 per unit. So the average cost is in dollars per unit. Okay, so if you produce 50 units per day, that would be as good as you can do for your production process. And your minimum lowest average cost per unit then will be $48 per unit. Okay, now, so that's how we go about answering something like this. Okay, I guess you could say there's three elements. First, we need like whatever kind of function you're talking about. If you're talking about minimizing revenue, you need a revenue function. If you're talking about minimizing cost, you need a cost function. If you want to maximize profit, you need a profit function. So you need a function for whatever it is you're trying to maximize or minimize. Okay. All right. And then if you find the critical number and verify that the curve is concave, either up or down, depending on whether you're trying to find a maximum or minimum, then you've got it. You get your answer from there. Then the last part would just be to state your answer specifically to whatever the question was asked. So the answer is not really 50. It's that the production level that's the best is 50. Okay. Now, I'm going to make several videos covering other kinds of problems like this. So I wanted to show you real quick. Here I'm on my math lab and I just went to assignment 3.2 and I'll pick another question here more or less at random. And so this one sounds different. It says a disease has hit a city. The percentage of the population infected T days after the disease arrives is modeled by this function, okay? Now, we don't know where that came from or why this happens to model the spread of the disease or, that's just not given. But such models exist and people with the right expertise and training can come up with them, okay? But we have to accept that. Our question is, after how many days is the percentage of infected people at a maximum? So when's this disease, as it spreads throughout the community, going to reach a peak? From that point on which it will go down. So you see how that's the same thing, but we're trying to find a maximum. So to solve this problem, we would find whatever the critical number is on this curve, and then after that, we would verify the curve is concave down. Okay, that's the shape it would have to have a maximum. Now, I'll do more of these questions. This video is just an introduction to the procedure. Okay, all right, so stay tuned for additional videos on other problems from that assignment. And I think from there, this first step might differ quite a bit to get that function that you're working with, but the second and third steps will remain the same.